Types of fluid models. Section on Fundamental Concepts in Fluid Mechanics. Because fluids move in complex ways in nature, to start to understand and explain some of the phenomena, we have to simplify some things. Before getting into models that were simplified in order to calculate, understand, define, and predict fluid movement, or just stationary fluid for that matter, we have to talk about some of the parameters fluids have. For now, we are just going to talk about the parameters we are going to be neglecting in order to classify these theoretical fluid models. First thing we have to talk about is viscosity. Now, the word viscosity comes from the Latin word viscum, which means mistletoe, which is a type of tree. And viscum, a type of glue made from the berries from this tree. We can see the berries on the picture on the left. So, glue, viscosity, let's define viscosity. What is viscosity? Viscosity is the resistance of a fluid to change in shape or movement of neighboring portions relative to one another. Viscosity denotes opposition to flow. So for liquids, it is visualized as the liquid's thickness, let's say. For example, here we have a GIF of two different types of liquids. On the left, we have water, and on the right side, we have honey, for example, because it matches the color. Honey is much more viscous than water, and that means it is going to resist flow more than water. And the thing about viscosity is that it is often mixed with density when we observe liquid flow. For example, here we have olive oil. Now, olive oil runs thicker, meaning it is more viscous. And we often treat fluids that run thicker as denser. But the fact is that olive oil actually has a lower density than water. So remember, next time you see a fluid run slowly, it doesn't necessarily mean that it is dense. It just means it's more viscous. We are going to be talking in depth about viscosity in the next section, the section on physical properties of fluids. But for now, let's give a simple and superficial explanation for it. We observe a fluid as a collection of molecular plates stacked upon each other. These are on a molecular level, and it is a natural occurrence for fluids to move in such a way when presented with shear stress. So a more viscous fluid would have these movements lower. In other words, this shear stress has to be larger in order to move the second layer of the fluid. So if we apply shear stress, if we apply a force, it's going to move like this, and it's going to take the next layer with it. This is a superficial explanation. We are going to talk more in depth in the section on physical properties, and there's going to be a lot more math involved. The second property we have to talk about is compressibility. Compressibility, as the name suggests, is if the fluid is compressible. But what does that mean? Well, that means that this is an ability to reduce the size, volume, of a fluid when a pressure is applied. One simple question. Would it be easier to compress a gas, air for example, or a liquid, water for example? Think about it a little bit. So finally, let's discuss these fluid models. We have these not just to make our lives easier as engineers, but to start to explain the complex ways of how fluids act. As we said in the beginning of the lesson, we have to simplify some things. And this is what we are kind of doing with these fluid models. We are simplifying them by neglecting a certain property to make them easier to calculate, predict, and analyze. First off, we have the ideal fluid. The properties that we neglected when incorporating such a fluid in our calculations are the viscosity and compressibility. So an ideal fluid would be non-viscous and non-compressible. An incompressible fluid, as the name suggests, is a fluid that is incompressible. In my course on hydraulics, we talk about hydraulic oils being incompressible, but the actual reality is that they are compressible. It's just that the compressibility factor is so low that we neglect it. Incompressible fluids can be viscous or non-viscous. Now, compressible fluids. Compressible fluids, again, as the name suggests, are fluids that are compressible. This is a model that is frequently used with gases, especially in fluid dynamics of gases. Usually, they are observed as non-viscous. And of course, the real fluid, which is not a made-up model, but a real-world fluid. It, of course, has both of these properties. It has viscous elastic forces present as well as the compressibility factor. Now, some fluids are more compressible, like gases, and other fluids, like liquids, have negligible compressibility factors, like water, for example. So the question from the previous slide, would it be easier to compress air or water? It would be easier to compress air. And air is much more compressible than water. Okay, this is it for the lesson on types of fluid models. Let's recapitulate the materials from this lesson. So an ideal fluid is a theoretical set of limits to help us calculate and predict the behavior of a fluid. Ideal fluids are non-viscous and non-compressible. An incompressible fluid is a fluid which always has a constant volume, no matter the pressure. Can be viscous or non-viscous. A compressible fluid is a fluid which has a variable volume. Usually it is taken as a non-viscous fluid. It is often used in fluid dynamics for gases. And real fluid has viscous forces and is compressible. Limited in terms of explanations. And when we say explanations, we mean the math behind it. This is it. Thank you for your attention and see you in the next lesson.